Alright, silly people, here's the situation. We have a wave function for which we are going to basically just calculate everything. We're going to normalize it. We're going to find the expectation value of position, momentum, the expectation value of position squared and momentum squared, find the standard deviations for position and momentum, and check that it lines up with Heisenberg's uncertainty principle. So, to do the normalization, we're going to be taking the integral from infinity to infinity. That just means either side of the bounds of the problem, which is minus a to a in this case, of the square modulus of the wave function, integrated over position. And that's going to be set equal to 1. That's how we're going to get a. So for us, that's going to look like a squared minus a to a of little a squared minus x squared squared dx. There are ways to do this integral in fast steps, but I'm just going to expand the square. So it's going to be a fourth minus 2a squared x squared plus x fourth. That's what we're integrating. And that's not too bad of a little power law integral. So it's a fourth x minus 2a squared x cubed over 3 plus x 5 over 5. And we're going to evaluate from minus a to a and set it equal to 1. So we'll have a squared a fifth minus 2a fifth over 3 plus a fifth over 5 minus, or plus actually, a fifth. So plus a fifth minus 2a fifth over 3 plus a fifth over 5. So all these add up. All these things add up pretty much. So we'll factor out a 2, and we're also going to factor out a 5. And what's left inside is 1 minus 2 thirds plus a fifth. Set that equal to 1. So we'll have 2a squared, a fifth. 15 minus 10 plus 3 over 15 equals 1. 15 minus 10 plus 3 is 8. Multiplied by 2. So you get 16 fifteenths. And now just solve for a. So a is going to be 15 over 16a to the 5th under a square root. Glorious. So then the expectation value per position is going to be, as always, from the bounds, you do psi star x psi dx. For us, it's going to look like minus a to a, forgetting not to the a squared, so this is going to be 15 over 16a fifths on the outside, fifth. Minus a to a minus x squared, it's a squared minus x squared, times x times a squared minus x squared dx. So it's going to be the same polynomial that we've had before, just multiplied by additional value of x. So it's going to be a fourth x minus 2a squared x third plus x fifth. That's what we're integrating. We'll do the integration again. It's just another power law integral. That's going to be a fourth x squared over 2 minus a squared x fourth over 2 plus x sixth over 6. That's from minus a to a. Evaluating this, we're going to have 15, 16 a-fifths. You're going to have a sixth over 2 minus a sixth over 2 plus a sixth over 6 minus a sixth over 2 plus a sixth over 2 minus a sixth over 6, which, I mean, this cancels out this cancels out this cancels out that, so it's all 0. Fine. It's nothing new. We have x squared will be from minus infinity to infinity of psi star x squared psi dx, which now is looking like, forgetting not the a squared out front, from minus a to a, it's going to be a minus x, it's both squared, times x squared times a squared minus x squared dx. So it's the same polynomial we've been getting, but multiplied by another power of x. So it's going to be the integral of 15 a-fifths. You got minus a to a. You got a fourth x squared minus 2a squared x fourth plus x sixth. And look at that, it's another power law integral. Not too bad here. This is going to be a fourth x third over 3 minus 2a squared x fourth over 5 plus x 7 over 7, and it's actually going to be a 5 here. That's going to be evaluated from minus a to a. So we got 15 over 16 a-fifths. We got a 7 over 3 minus 2 a 7 over 5 plus a 7 over 7 plus a 7 over 3 minus 2 a 7 over 5 plus a 7 over 7. So again, they all just kind of add up. So we got 15 over 8a5, just factoring out a 2, and also factoring out an 8 to the 7. We have 1 third minus 2 fifths plus 1 seventh. Prefactor outside simplifies to 15a squared over 8. And then we're going to have to find a common factor for these. So common factor, just multiply everything by the other denominators. So it's looking like 35 minus 2 times 21 is 42, plus 1 times 15, so 15 over, what is 3 times 5 times 7? I wonder. $105. Okay. Continuing to simplify, 15a squared over 8 out front. That fraction is, just gonna use a calculator. That's 8 over 105. Okay, so the 8's cancel out, so we have 15a squared over 105. And then, does that reduce at all? We can divide both of them by 5, and you get 3a squared over 21. You can divide both of those by 3, so you get a squared over 7. I think that's about as good as it gets. Okay, and then so the expectation variance, or the standard deviation of x, as always, is given by the expectation value of x squared minus the squared expectation value of position. We found this value is 0. This is 7 over 7. So no, a squared over 7. Be careful with that. So it's just the square root of a squared over 7. And we'll leave it like that for now. Moving on to expectation value of p. You can't use Ironfest's theorem for this because we found that the expectation value of x was 0. So if it was non-zero, then we could just say that it's just m dx dt, because that's the definition of momentum in classical physics. But again, it's 0, and we can't really take a expectation value of 0. So then expectation value of p is going to be minus infinity to infinity of your conjugate wave function times the momentum operator times your wave function integrated over position. So for us, it's going to be minus a to a, remembering to write down the normalization constant, minus infinity to infinity, or minus a to a, actually. That's looking like a squared minus x squared, and then the momentum operator is just IH bar del x of your wave function. So we got 15 IH bar over 16 a fifth minus a to a. That derivative is just going to be minus 2x. So we have minus 15. I'm actually going to, minus 15 IH bar over 8 a fifth. And then we'll move that x into the polynomial. So we have a squared x minus x cubed. And then we can integrate that. It's going to be a squared x squared over 2 minus x fourth over 4 from minus a to a, which evaluates to a fourth over 2 minus a fourth over 4 minus a fourth over 2 plus a fourth over 4. Cancel, 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 cancel. It's 0. Expectation value of momentum is 0. That's fine. We can say expectation value of p squared now, which is from minus infinity to infinity of your psi star, and then it's the squared momentum operator dx, which is gonna look like h bar squared over 2m. No, not just over 2m. It's just minus h bar squared. And then in the integral, you're going to be doing a second derivative with respect to position of your wave function and integrating over it. So for us, that's going to look like minus h bar squared, 15 over 16 a fifth. You have the minus a to a, you have the a squared minus x squared, you have the second derivative of a squared minus x squared dx. So that's looking like, so we already know that the first derivative is minus 2x, so I'm going to factor out a 2 and a minus sign first of all. So you have 15h bar squared over 8a squared, a fifth actually. Minus a to a, you'll have a squared minus x squared del x of x dx, which is just 1. So you're actually just taking the integral from minus a to a of a squared minus x squared, which is looking like a squared x minus x third over 3 from minus a to a, which is looking like 15h bar squared over 8a fifth. It's going to be a third minus a third over 3 plus a third minus a third over 3. So factoring out a 2 again, we have 15h bar squared for a fifth, and we can also factor in a third at this point. You'll have 1 minus 1/3, which is 2/3. So we'll have 15h bar squared a. Actually, some of the a's will cancel out, so you'll have 4a squared on the bottom. And then so this is 2/3. That simplifies. So 15 over 3 is just 5. 2 over 4 is 1/2. So it's h bar squared, 5h bar squared over 2 a squared. And so, yeah, that's your expectation value of momentum squared. The standard deviation then will be expectation value of p squared minus the squared expectation value of p, which we found this value was 0, so this is just the square root of 5h bar squared over 2a squared. Last, we can check if this obeys Heisenberg's uncertainty principle. That is, sigma x, sigma p better be less than or equal to h bar over 2. It's greater than or equal to h bar over 2. So for sigma x, we just got a squared over 7 under a square root. For sigma p, we just got 5h squared over 2a squared. Funnily enough, this a squared cancels out this a squared, so it doesn't depend on a squared, so that's nice. So we'll have h times the square root of 5 over 14. And the square root of 5 over 14 is greater than 1/2. If you like, it's exactly equal to like 0.05, no, just 0.5976, which is greater than 1/2. And so our expectation, or our standard deviations multiplied together are greater than h bar over 2. So Heisenberg's uncertainty principle is satisfied. Okay.